All right, now we're going to go ahead and get the electric field due to this ring of charge at this point P. One of the things I want to point out is there is a little bit of cancellation of vectors here. So first, the total charge on this ring is equal to Q. That's the total charge. But we're going to work in terms of what we call the linear charge density, which is going to be the total charge divided by 2 times pi times r. We're taking this charge and we're smearing it across the circumference. And so what this means is if I have this little chunk of circumference here, then dq is going to equal lambda times ds. And by the way, if you go all the way around the circle, it's 2 pi r. Lambda times 2 pi r gives us our total charge Q. So one small thing we should point out is that the electric field at point P actually has two components. There is a little dEx component, and there is a dEy component. And here's the problem. They give us the angle theta. So when we actually do SOHCAHTOA here, this component here is dE sine theta, and this component here is dE cosine theta. And I just want to make a point here that why is cosine theta? Because the book uses an annoying angle. I'm blaming the book. So here's why we care. Check this out. This little ds produces a field, right? But it turns out on the other side of the ring, there's an exact opposite side ds, and it's putting a field up the opposite way. And when we actually label it, what we get is that there is a dEx here that's the same size and a dEy. And so what we're getting is this dEx cancels out with that dEx. So by looking at this picture here, what we see is only Ey, whoa, gross, only Ey matters. And to see why, I'll say see the picture. Okay. So what this means is we're going to actually have to calculate this Ey, this dEy is going to equal dq over r squared 1 over 4 pi epsilon naught. And what we're going to need here is the cosine of theta as the component that we do because we're just doing Ey for the total E. And then to get E in the y direction as our total field, I'm going to take 1 over 4 pi epsilon naught. I'm going to integrate dq over r squared times the cosine of theta. And I'm going to write an integral here, and I'm going to be clear, this is actually a definite integral. And here's what's nice. In math class, you need to have 0 to 2 pi r or whatever like this. You need to have specific endpoints. I'm just going to do a little physics cheat and say I'm going to integrate around the circle. Okay, I'm allowed to do that. I guess if you want, we could say we're going from theta equals 0 to 2 pi. So here's what we're going to do. I'm not even going to be evaluating these limit points anyway. You're going to see how this works out. It works out really nicely. with the arc length in a second, you'll just see. So let's just measure r. I used little r here, okay? And let's be clear that that's actually equal to r squared plus z squared under a square root. And I'm actually going to put that into my formula. So I have EY equals 1 over 4 pi epsilon naught. Sorry, it's just gross. 1 over 4 pi epsilon naught. dq, again, is lambda ds. R is going to be this value right here, r squared plus z squared, okay? That's just the r squared substituted in, times cosine of theta. Now, when I look at how I get cosine of theta, notice z over r is the cosine of theta. And I'm going to integrate this all the way around the circle. So just kind of continuing on this wonderful little trend. And you know what, I'm just going to put a little r here for my limit point since I'm going to integrate around the circle. I thought it was an angle, but whatever. So here we go. E then, I'm going to drop the y because this is the total field. Okay. So 1 over, so I'm just going to say drop this. We don't need it. 1 over 4 pi epsilon naught. And we're basically just going to say that this is z times lambda. And let me make absolutely sure that I got the cosine right. I said z over r is cosine theta. Careful. I need adjacent over hypotenuse. This is actually z over little r. Let me make that little bit of a correction there. That z over little r, this is going to be z over little r right here, because there's a small little correction I need to make. When I plug this in, this is z lambda r squared plus lambda ds, sorry, r squared plus z squared. Cosine of theta is going to be z over. Now when I have the little r here and I expand that out, or I write in what r is actually in terms of the triangle, that's going to be r squared plus z squared under a square root. Sorry, I have an extra z here that I don't need. Yeah. So, continuing here, we have E equals 1 over 4 pi epsilon naught sorry, this pen's being weird. So, E equals 1 over 4 pi epsilon naught. And now, let's get all our terms together. Notice z doesn't change and r doesn't change. They actually stay constant throughout the whole problem. So I can actually treat them as constants. So I'm going to get z over, and on the bottom here, r squared plus z squared to the 3/2. I'll also factor out the lambda times ds integrated from 0 to 2 pi r. So finally, I'm going to end up getting an electric field equal to 1 over 4 pi epsilon naught z lambda times 2 pi r. I'm going to factor that, and you'll see why in a second. Because basically ds integrated is s from 0 to 2 pi r. Put that in there. Over r squared plus z squared to the 3/2. Lambda times 2 pi r, well, that's just our charge. So we end up getting an electric field equal to 1 over 4 pi epsilon naught q times z over r squared plus z squared to the 3 halves. All right, so that is actually how we get the field due to a ring of charge. You'll need to review that a few times, and it'll actually give you a better write-up kind of typed out. But I do want you to follow and write down this proof as part of your homework.